This is Monterrey City, a place that hosts around 4 million inhabitants who work every day to improve their quality of life. Nonetheless, in recent years, the concentration levels of pollutants like carbon and nitrogen-based gases in the city have increased exponentially thanks to the immense industrial power the urban area is holding. Besides, this is a problem that is not only visible in Monterrey City nor Mexico. It is a worldwide problem that has caused millions of deaths in years. This has reached an unthinkable magnitude, even that all it takes to notice the problem is to take a look at the Cerro de la Silla, the most famous mountain in Monterrey, and see the huge smoke clouds blocking its view. It has been proven that the increase of these contaminants has been induced by the increase in the industries assembling in the city, the unsuitable urban transportation system, and the accelerated population growth, causing allergies, airborne respiratory disorders, among other health concerns. After consulting with the citizens, and despite the fact that there have been proposed governmental strategies to mitigate this problem and analyzing the current physical, chemical, and biological methods, it is noticeable a lack for innovative solutions to the problem during the last years. Therefore, inspired to improve air quality for the citizens of Monterrey, we decided to develop a bio-inspired proposal. For this, we created CO No More, an alternative air biofilter system that will be capable of decomposing some of the principal air pollutants present in Monterrey's air. These compounds are clearly seen as a threat because they all affect citizens' health and lifestyle. The proposal takes into account synthetic biology principles since it opens a new world of possibilities for problem solutions, making them more accessible and environmentally safe. Thus, increasing the visibility of this type of projects is no longer an option but a need.
No More is based on a biofilter design which incorporates the use of bacteria that are capable of producing recombinant enzymes that degrade the major carbon and nitrogen pollutants present in Monterrey, which are carbon monoxide, carbon dioxide, nitric oxide, and nitrous oxide, which are also representative compounds of the greenhouse emission gases. For the development of our design, we have been inspired by previous strategies proposed by former iGEM teams, and we have implemented part of them. After this, we designed two models that decompose the carbon and nitrogen compounds to eco-friendly compounds respectively, based and constantly developed throughout the engineering cycle principles. In the carbon compounds model, two enzymes with sequential reactions are used: carbon monoxide dehydrogenase and carbonic anhydrase. Carbon monoxide dehydrogenase allows the conversion of carbon monoxide to carbon dioxide, while carbonic anhydrase breaks down the carbonic dioxide into bicarbonate. Although the production of carbon dioxide sounds counterproductive, the expression of the enzymes will be regulated so that the production of carbon monoxide dehydrogenase is less than the carbonic anhydrase. In this way, the transforming ratio from carbon dioxide into bicarbonate will be higher than the transformation ratio from carbon monoxide into carbon dioxide, allowing to prevent the carbon dioxide accumulation. This is also related to the concentration levels of carbon monoxide and carbon dioxide, since carbon dioxide is found at a higher level than carbon monoxide in Monterrey's environment, and it is also the intermediary for the carbon monoxide transformation. We expect to express this system in E. coli, since these enzymes already have experimental confirmation for a positive expression in this organism. The same case occurs in the nitrogen compounds model, since there are two enzymes, nitric oxide reductase and nitrous oxide reductase, where one is less expressed than the other respectively. Nitric oxide reductase converts nitric oxide to nitrous oxide, and subsequently nitrous oxide reductase degrades nitrous oxide to atmospheric nitrogen. The concentration of the nitric oxide compounds is fewer in Monterrey's atmosphere than nitrous oxide compounds, and nitrous oxide will act as an intermediate for the nitric oxide degradation. It is worth mentioning that in addition to these enzymes, the nitrogen-based model will also feature a coding sequence for the NNR transcription factor, which allows the system to be responsive to any nitrogen-based oxide. The regulation of the expression of these enzymes is mediated by their promoters, since the selected promoters are each inducible to the environmental concentration of the compounds mentioned, respectively. The carbon model is based on two promoters. As shown, the promoter PCOM is inducible under carbon monoxide concentration, which it has been reported for having a low capacity for genetic expression. Meanwhile, the promoter PM9 is inducible under carbon dioxide concentrations, and it has a higher capacity for gene expression. PCOM and P9 regulate the expression of carbon monoxide dehydrogenase and carbonic anhydrase respectively, and it favors the reaction of carbon dioxide into bicarbonate to prevent carbon dioxide accumulation. For the nitrogen compounds model, the regulation strategy was implemented similarly. The promoter P near S is inducible under nitric oxide concentrations with a low gene expression, while the promoter P nor C is inducible under nitrous oxide concentration with a higher gene expression. P near S and P nor C regulates the expression of nitric and nitrous oxide reductases, respectively. Thus, this regularity system allows a higher transformation from nitrous oxide to molecular nitrogen, preventing nitrous oxide accumulation.
After searching for those enzymes capable of degrading the pollutants of interest, able to work with our expected conditions, as well as the genetic regulatory elements involved in the production, we brought forward in our design the way in which we could implement the operation of the proposed biological system in reality. For this purpose, we chose to design a device that contained our system to perform the function for which it was designed. After studying different types of biofilter designs, we approached Juan Pablo Martinez, a stakeholder with experience on biofilter design. After studying the characteristics of the main used biofilters and suggestions by Juan Pablo, we determined to develop a biofilter design based on a fixed bed with cover, since it has easy operation, low cost of investment, supports long period without feeding, suitable for intermittent operation, and does not produce water disposal. These characteristics are ideal for our design, since it allows greater accessibility and lower maintenance costs for implementation in different sectors around Monterrey. We approached expert stakeholders on the field, Juan Pablo, Diana Bautista, and Jorge Uribe, people with experience in the development of mathematical models and biological behavior focus, who assisted us with finding appropriate equations and data for mathematical approximation of the behavior of our expression system in our biofilter. The explanation of our strategy on the use of genetic circuits is supposed to be given in a single strain of our chassis, Escherichia coli. Nonetheless, an important question as part of our biofilter design is whether it is necessary to compartmentalize our chassis into two strains, so that one strain is able to degrade carbon compounds, while the other strain is able to degrade nitrogen compounds. For this, we approached with stakeholders Engineer Asael Martínez de la Cruz, Engineer Edith Luevano Hipólito, and Adán Ramírez Sánchez, Chief Executive Officer from Green Fluidics, who have knowledge and experience with air purification and air pollutants degradation, where they mentioned to us that ideally all the circuits would be in a single strain. Therefore, our proposed mathematical approach from gene expression modeling in our biofilter has two important goals based on the suggestions of our stakeholders. The first objective is to know if our circuits will act as expected, that is, that the concentration of enzyme production is in accordance with the weak and strong promoters selected. The second objective is to know if the best approach is to join all the circuits in a single strain, or if it's necessary to compartmentalize the circuits of the respective compounds into two different strains. First of all, our results show that the production of the enzymes does agree with what is expected. The production of the enzymes carbonic anhydrase and nitrous oxide reductase are higher produced, since they are the important step towards the degradation of pollutants to environmentally friendly compounds. In addition, the result of enzyme production indicate that if all genetic circuits are focused in a single strain, this cell will have a high stress content and high energy requirement. Therefore, the best option is to compartmentalize our chassis into two modules to provide optimal production conditions. It is important to mention that these initial mathematical approximations use differential equations based on time and not on the geometry of the biofilter. Therefore, one of our future perspectives is to use more exact mathematical models, resulting with higher approximation based on our biofilter dimensions.
A biological risk assessment was developed according to national and international regulations. For this, we consider the risk of the biological parts used for the elaboration of the GMO, laboratory accidents, risk that the chemical agents represent, possible ways of escape of the microorganism from the filter, methods of detection of the microorganism in case of escape, formation of biofilms, horizontal genes transfer, and survival in the environment. It was concluded that the risk estimate is very low, because all the parts that are intended to be used do not represent any virulence factor or have been related to disease in humans, animals, or damage the environment. Regarding the biological approach of Project Human and Environment, Well-being and Compliance of Laws and Regulations, a kill switch was designed to ensure the biocontainment of the GMO in the event that our organism will escape from the laboratory or the biofilter to avoid horizontal gene transfer. In our proposal, we choose a kill switch for biocontainment of our chassis based on the expression of hog toxin, which will be under the control of an inducible UV promoter, which will begin expression when the bacteria get exposed to the light and thus kill them. On the other hand, SOC expression will be under the control of an arabinose promoter, allowing the bacteria to remain viable when sampling or culture handling is required by simply adding arabinose to the medium. We choose this kill switch since the biofilter will be exposed to light. In this way, it will be possible for us to regulate the expression of an antitoxin in the medium, and thus ensure that the bacteria only survive in the biofilter thanks to the presence of a simple sugar in the medium, the arabinose.
For the development of our multidisciplinary activities that benefit the communication of science and our project in our regions, we have placed various conditions to implement them. First, the use of art and creativity for the creation of educational and communication content, and by inspiring for the outreach of our project in society, such as the use of eggshell to generate a biomaterial, as well as the use of pedagogical material that allows simulating and knowing biological processes in a visual way, from making a DNA model to genetic modification processes, among others. As well as inclusivity, since for us it is important to create an environment that is safe and equitable for all people, regardless of their ethnic group, country of origin, sexual orientation, race, ability, gender, age, or even personal interest. Finally, we carry out these activities based on compliance with the SDGs, since it is possible to cover a wide variety of objectives to benefit their progress. Important pillars, we have developed complete activities that favor scientific communication, such as our activities in schools and even nursing homes, raise environmental awareness, such as our photography contest to generate awareness about climate change, in which citizens across Chile, Ecuador, and Mexico participated, and introduced our project in our region, encompassing as many people as possible, where the participation of preschool children, youth, and elderly adults stand out. For us, the knowledge and dissemination of science must be accessible to all.
Through the development and validation of the biofilter design as well as safety features, a business plan was developed to learn about the current market where an opportunity for development was found, since Latin America, especially Mexico, is an ascending developing region in the implementation of alternative air filters and air quality standards and management. For this, we developed the proposal Conomore, a company interested in reducing carbon and nitrogen compounds emission through the use of a biomass-based air filtration system, product and service, developed with synthetic biology and biotechnology, which is mainly focused on the implementation in the most environmental pollutant sectors in the Mexican northeastern region, and it is hoped that under the scaling and positioning of our product in the market, it can reach more affected regions in Latin America and worldwide. We approach our stakeholders as El Martinez, Edith Ruebano, Alan Ramirez, Juan Pablo Martinez, and also Ray Eliud Dimas Granados, who has experience in promoting youth entrepreneurship. They allow us to be able to validate our business model and also put it into a narrative that is adequate under the principles of bioeconomy and the Sustainable Development Goals. We aim to take action into three main objectives. Number 9, industry, innovation, and infrastructure, by reducing the impact of industrial activity on the environment without affecting the benefits it can bring to society. Number 11, sustainable cities and communities, by reducing the amount of carbon and nitrogen elements released into the environment. And number 13, climate action, by reducing the concentration of greenhouse gases. It is important to mention that by participating in the iGEM Design League competition, it allows us to be in contact with various teams around Latin America to put into action the CDG 17, by forming alliances for the fulfillment of the CDGs, by collaborating with the improvement and development of the projects as well as of different activities. The team is committed to benefit the development of sustainability in our region and fulfill our proposed objectives, not only with our project approach, but also with multidisciplinary activities that complement environmental awareness and science communication.
The implementation of a structured path towards our objectives has allowed us to develop our Kunomore project under structured and defined follow-ups, which allow us to know the progress of our proposed design. The next steps for our project will be to keep improving it by finding better suitable components for the biofilter structure that allows optimization and performance, more detailed mathematical approaches, and studying viability and degradative performance during prototype scaling and field testing plan, in which it is expected to improve bioeconomy in our region. Keep validating the project in the new areas that arise, such as approaching enterprises that produce biofilters and communicating with more enterprises in the industry target areas. Diversify our science communication activities for wider communities and strengthen our commitment to compliance with the SDGs. With the future perspectives that we have contemplated, we hope to put them into practice in the following years, which will allow Kunomore to benefit the air quality for thousands of people in Monterrey, and unify our preservation towards the mega biodiversity across the region. This is Kunomore by iGEM FCB UANL 2022.